So in the previous part of the lecture, we had seen that by regulating the values of W, like that is by regularizing the regression problem. So let's assume we are assuming uh, a linear model, that is yi is given by some function mapping fw of phi of xi plus some small noise, where this is a linear model. Then what we get is a linear regression problem. And if we assume that that these noises have Gaussian prior or the Gaussian distribution, then what we get is the least squares problem, that is y minus phi times w square. And by assuming a prior on the parameters w itself, what we get is regularization. So in Bayesian setting, we have priors, different priors, and different priors lead to different kinds of regularization. For example, a Gaussian prior will result in L2 norm regularization, and a Laplacian prior would result in L1 norm regularization. So both of these, as we have seen in the previous in the previous part, both of these norms have a tendency to decrease the value of w, to regulate the value of w, right? So for example, in this particular case, we have exp of negative of in case of a scalar variable, we have w square, and in this case we have exp of negative of absolute value of w, the Laplacian, the Gaussian prior and the Laplacian prior. So as we can see, both have a tendency, when the w is large, then both will be very small, and the resultant probability of w having that value would be very small. So this would have a so this would penalize the objective function to decrease the value of w, right? So by having different kinds of prices, we receive different kinds of regulation. But how do these two differ from each other, right? When both decrease the value, how do we know which one is better for doing regularization? So let's see how they differ actually. So what we are going to show is a very crude representation of what is going to happen in the optimization procedure. This is not the accurate representation. This is just a crude approximation of what is going to happen to let you understand as to how these different priors play a role in regularization. So let's assume if the W is a scalar. So let's first plot the Laplacian distribution. With mean 0. So this would be exactly symmetric, but we are not able to like draw. So this is a crude representation. And now let's plot the Gaussian distribution. Again, this would be symmetric, but just assume that this represents the symmetry. So as you can see from the plot, the Laplacian distribution has much larger tail as compared to a Gaussian distribution. This is because in Laplacian we have exp of negative of absolute value of w, and in Gaussian we have exp of negative of w square. So when w is large, let's say w is 100, the Gaussian will be e to the power negative of 10,000, and the Laplacian will be e to the power negative 100, right? So as you can see, the Gaussian distribution will drop very quickly as compared to a Laplacian distribution for the larger values. We know that both of these distributions will try to draw the w close to 0, right? But as you can see, once in case of Gaussian distribution, once we near towards 0, once the w sort of like gradually goes towards the 0, the gradient almost flattens out, right? So in a sense, the Gaussian distribution finally gives up on drawing the values further close to zero. So after some point, this the Gaussian prior will have almost negligible effect once the values are sufficiently close to zero, right? So in this case, in case of an L2 norm regularization, what we'll see is that we will have many values in the weight vector close to zero, but they will not exactly be zero, right? But in case of a Laplacian prior, right, as we go close to zero, the gradient becomes sharper and sharper and sharper, right? But since we take log of the likelihood, here you can see in case of L1 norm, the gradient is given by just +1 when W is greater than 0 in case of a scalar, -1 when W is less. This is because we have taken the log, right? But in actual, and that's why we said this is very crude approximation of what is going to happen in the optimization problem. So from the graph, what we can see is that as we move close to zero, the gradient sort of becomes sharper actually, right? So the Laplacian prior has an effect of drawing most of the values of W exactly equal to zero, right? So what you will find with Laplacian prior is that most components of the W are exactly equal to zero, right? And Laplacian prior allows many values to assume a large value as it has much fatter tail as compared to a Gaussian distribution, right? And that's why when we have L1 regularization, since we are going to have lot of W's as zeros, right? That's why sometimes this L1 regularization is also known as feature selection in the machine learning literature, like a feature selection procedure, feature selection algorithm. Because if the weight corresponding to some feature is zero, it means that feature plays absolutely no role in the regression problem, right? And that's why we say that this tends to select feature, and that's why sometimes we call it a feature selection, right? So now that we have given an overview, so what we have understood so far is that in the previous lectures we assumed that the W was some unknown variable but not a random variable, whereas the Bayesian setting allows us to model this W as a random variable, and then we have some prior distribution of over the parameters W, and after multiplying this with the likelihood and the max, and then taking the log and log of the resulting equation, what we receive in the end is that different kinds of priors lead to different kinds of like optimization formulation or different kinds of regularization, right? So by having L2 norm regularization and L1 norm regularization, we regulate the values of W, we draw them close to zero, and L1 norm will have an effect of most of the values being exactly zero, whereas L2 norm will have an effect that most of the values will be very close to zero, but they will not exactly be zero, right? And now, since we have formulated these optimization problems, that is L2 norm regularized least squares, which is minimizing. So here W is given by arc min over W, norm of y minus phi times W square plus some lambda times, which is a hyperparameter. And towards the end of this lecture, we'll see how to select the value for the parameter lambda times the L2 norm square of the parameters. Whereas the L1 norm regularization, L1 norm regularized least squares has the resulting optimization problem as W equal to arc min W, norm of y minus phi times W square plus lambda times norm of W1. So far we have taught you the importance of regularization, how regularization controls the model complexity and allows us to prevent overfitting of fairly complex models over the noise in the dataset. We've also given you the probabilistic interpretation of these regularization formulations in the Bayesian setting, and we have also seen like how can we incorporate different kinds of priors over the pointed W, and we also seen that we can obtain a posterior distribution if we could compute the integral that we had seen in the previous parts of lecture. Then the Bayesian setting allows us to also compute the posterior the distribution over the target values for any new input data point if we could compute the integral. Whereas if we cannot, then we can obtain a single value of W that given a new input can predict its corresponding target value. And these are the two formulations. This is L1 norm regulation, L2 norm regulation. And now we will study the algorithms to solve these optimization problems. So obviously in the previous lecture, we have seen that the least square problem has a nice closed form solution, right? And it turns out that the L2 norm regulation also has a closed form solution. So we can compute the optimal W by both using gradient descent as well as a closed form solution. But for the L1 norm regulation, there is no closed form solution. Right. And we have to use an iterative algorithm, and furthermore, this is a non-differential objective function because the norm of W1 is not differential at W equal to 0. That's why the overall problem is not differentiable. So we can optimize it using what is known as subgradient descent algorithm. But it turns out that subgradient descent in its naive form would be very slow at minimizing this loss function to obtain this value of W. And that's why we have a better algorithm which is known as iterative soft thresholding algorithm, or also known as ISTA, I-S-T-A. So next, to understand more the ISTA algorithms and the subgradient descent formulation, first of all we will take a detour or a small deviation to understand the convex functions, the convexity, what does it mean to, what are the first order convexity conditions, and we will derive them as well, we will prove them as well. And then we will study what subgradients are and how we can use subgradient descent to solve this problem. And then finally, once we have all the mathematical tools to actually understand and derive this ISTA algorithm, we will show you how ISTA can be used to not just solve the L1 norm regulation problem, but to also solve the least squares problem in a much more effective manner.